Okay, so for the proof of this one, let's skip the proof because we did the proof for product rule. So this is almost similar to that. You can do it as an exercise. Proof. Exercise, again, you can call this f of x over g of x. You can call it h of x. And try to find limit h of x plus t minus h of x over t as t approaches to 0. And prove the quotient rule. Okay, so let's look at some examples. Let's say let g of x be a differentiable function. And let's say g of x is not equal to 0. Find the derivative of, let's say, 1 over g of x. So is the derivative of 1 over g of x. We can easily use quotient rule. So what is derivative going to be? So 1 over g of x. Derivative is going to be 1 derivative times g of x minus 1 times g prime of x over g of x the whole squared. Now, 1 derivative of a constant function is 0. So derivative of 1 is 0. So it's going to be 0 times g of x minus g prime of x over g of x the whole squared. So 1 over g of x derivative is minus g prime of x over g of x the whole squared. So for example, let's say if you want to find, let's say y equals 1 over x, find dy to dx. So how can we do this? So dy to dx, so dy to dx is going to be 1 over x derivative. So that's going to be 1 derivative times x minus 1 times derivative of x over x squared. So 1 derivative again is 0 and derivative of x is 1. So minus 1 over x squared. So we concluded that derivative of 1 over x is minus 1 over x squared. Similarly, we can find derivative of, let's say, x 1 over x to power m. How can I find derivative of 1 over x to power m? So we want to find dy to dx here. So derivative of 1 over x to power m. Okay, so we can do the derivative similar to the previous one. So dy to dx is, which means the derivative of 1 over x to power m. So we can say, use the quotient rule again. So 1 derivative times x to power m minus 1 times x to power m derivative divided by x to power m to power 2, right? So u over v derivative is u prime v minus u v prime over v squared. Then derivative of 1 is 0 again. So 0 times anything is 0. So minus 1 times derivative of x to power m is m x to power m minus 1 divided by x to power 2m, right? X to power m to power 2 means x to power 2m. And then how can we write this? We can write this one as minus m x to power m minus 1 minus 2m. So 2m, we can subtract the power, and then we'll get minus m x to power minus m minus 1. Right? Because m minus 2m is minus m. So we showed that derivative of 1 over x to power m, which is x to power minus m derivative, right? Because 1 over x to power m is same as x to power minus m. So what was the derivative according to our calculation? The answer is minus m x to power minus m minus 1. So let's say if I call this minus m, if I call it L, let's say. So what can I say? If I call minus m and let's call it L, then I can say x to power L derivative is equal to L x to power L minus 1. See, remember we previously showed in the, I think, second rule, we showed that like x to power m derivative is mx to power m minus 1. And in that rule, we assume that m is a natural number. But here L is minus m, so it's a negative number, so negative integer. So in other words, we have generalized that rule, the rule number 2, to the set of all integers. So this means, so this implies that rule number 2, i.e. x to power m derivative equals mx to power m minus 1, is valid for every integer m. For every integer m is valid. Because first we showed it for natural numbers. Now here L is minus of a natural number, which means a negative integer. So this rule is also valid for negative integers. We previously showed it's valid for positive integers. But for 0, of course, is valid as well. Because if your m is 0, x to power 0 means 1. Derivative of 1 is 0. And 0 times x to power m minus 1 will be also 0. So it's also valid for 0. And valid for positive integers, valid for negative integers. Therefore, it's valid for every integer. Later, we will prove that this rule is valid for every real number m. So even if m is an arbitrary real number, not necessarily an integer, for example, let's say if m is root 2, what is the derivative of x to power root 2? We'll see that the derivative of x to power root 2 is root 2 times x to power root 2 minus 1. So x to power m derivative is mx to power minus 1 for every real number m. So far, we proved it for every integer m. Later, we'll prove it for, or generalize it to every real number m. All right, so let's look at another example. Let y equals, let's say, x cubed minus x divided by x squared plus 1. Find dy to dx. So how can we find dy to dx here? Dy to dx is equal to derivative of top, which is x cubed minus x times x squared plus 1. So u prime v, derivative of top times bottom, minus top, which is x cubed minus x, times derivative of bottom, divided by x squared plus 1 to power 2. U prime v minus uv prime divided by v squared. And then this will be what will be the derivative then? So x cubed minus x, derivative means 3x squared minus 1 times x squared plus 1 minus x cubed minus x times the derivative of x squared plus 1 means 2x divided by x squared plus 1 the whole squared. Right? So derivative of x cubed minus x is 3x squared minus 1. And then derivative of x squared plus 1 is 2x, because derivative of x squared, which is 2x, plus derivative of 1, which is 0. Now, if we simplify this further, so this is a 3x to power 4 plus 3x squared minus x squared minus 1 minus 2x to power 4 minus 2x squared divided by x squared plus 1 the whole to power 2. And how much is that going to be? So 3x to power 4 minus 2x to power 4 is x to power 4. 3x squared plus 2x squared is 5x. 5x squared minus x squared is 4x squared minus 1 divided by x squared plus 1 to power 2. 3x to power 4 minus 2x to power 4 is x to power 4. 3x squared plus 2x squared is 5x squared minus x squared with 4x squared, and then minus 1, and then divided by x squared plus 1 the whole to power 2. Okay, so this is the derivative of this function, which we calculated using the quotient rule. Now the next rule we can look at, so the seventh rule, let's say if you have some trigonometric function, let's say f of x equals sine x, then f prime of x is equal to cos x. Or let me say then f of x is differentiable at every point, and f prime of x is equal to cos x. So sine x is a function which is always differentiable. In other words, differentiable from minus infinity to infinity. And the derivative of sine x is cos x. Okay, so how can we prove this? Proof. So what is f prime of x? We need to, f prime of x is equal to limit f of x plus h minus f of x divided by h as h approaches to 0. Now, how much is that going to be? Limit f of x plus h means sine x plus h minus sine x, f of x is sine x divided by h approaches to 0. F of x is sine x, so f of x plus h will be sine x plus h minus sine x divided by h. So as we expect, we know that when we calculate derivative of a function, the limit of the fraction, if the calculation is correct, we need to always get 0 over 0, and then we have to simplify. Well, here, if I replace h with 0, I'll get sine x minus sine x, which is 0 over 0, which means we have to simplify. How can we simplify here? Well, we have a formula for sine of addition of two angles, sine x plus h. What is that going to be? So limit sine x cos h plus cos x sine h minus sine x divided by h. H approaches to 0. And then this is limit sine x times. Now, first and last term, sine x is a common factor. I can take it out. What will be left? Cos h minus 1. Cos h minus 1 will be left. And then plus cos x sine h divided by h. H approaches to 0. And then how much is this going to be? So this one I can write it as, see, the limit is over h. So sine x can be taken out because there is no h in sine x. It can be taken out of the limit. So sine x times limit cos h minus 1 divided by h. H approaches to 0. Plus, again, similarly, cos x can be taken out from the second term. So cos x times limit sine h over h. As h approaches to 0. Now, this limit, we have seen that it's 0. So this has been justified. Let's say was justified before. You know, when we were doing trigonometric limits, in the same lecture that we explained above limit sine h over h as h approaches to 0, we also showed that this limit is 0. If you look at the lecture or the lecture notes. So this limit is 0, and then this limit will be how much? So this limit sine h over h as h approaches to 0, it's 1. Right? This is again, we have seen it in the same lecture that we did trigonometric limits. A limit sine x over x as x approaches to 0, or limit sine h over h as h approaches to 0 is 1. So what will be the answer? The answer will be sine x times 0 plus cos x times 1. So the answer is cos x. So we showed f of x equals sine x is differentiable. And what is its derivative? And f prime of x is equal to cos x. Derivative of sine x is cos x. Okay, so let's look at an example. Let's say let y equals sine x over x. Find dy to dx. So again, we have to use the quotient rule, and we already know that derivative of sine x is cos x. We have to also use this fact. So derivative of quotient of sine x and x, according to the quotient rule, can be written as sine x derivative times x minus, so u prime v minus u v prime. So sine x times derivative of x divided by x squared. So that's going to be x times cos x minus sine x divided by x squared. U prime v minus u v prime divided by v squared. Well, that's it. So this is the answer, x cos x minus sine x over x squared. So this was for the derivative of sine x. Now, what about derivative of cos x? So the eighth rule, f of x equals cos x. And then we can say f of x is differentiable everywhere. And the derivative of this function, derivative of cos x, is minus sine x. Okay, so we said that derivative of sine x is cos x. Derivative of cos x is minus sine x. So this one for the proof, I can leave it as exercise. It's very similar to, we did the proof for sine x. This one is similar to that. For sine x, we had to use the addition formula for sine x plus h. We expanded it, and then we calculated the limit. For this function, of course, you have to use the addition formula for cos x. So cos x plus h, you have to expand it. And then calculate the limit. So the ninth rule for f of x equals tan x. Then f of x is differentiable at every point x with or such that or with cos x not equal to 0, right? And for these values of x, we can say that f prime of x is equal to secant squared x, which is same as 1 plus tan squared x. And that's same as 1 over cos squared x. Okay, so tan x, please remember that it's sine x over cos x. So of course, if cos x is 0, then tan x is undefined, and therefore, of course, not continuous or not differentiable either. But if cos x is not equal to 0, if denominator is not equal to 0, then we can say that f of x equals tan x is differentiable, and derivative of tan x is secant squared, and secant squared, it means 1 over cos squared, which can also be written as 1 plus tan squared x. So similar, so for proof this one is very simple. F of x equals tan x. You just need to write tan x as sine x over cos x. And then we can calculate f prime of x easily. Then f prime of x by quotient rule. We can write it as sine x over cos x derivative. So u over v derivative is u prime v, sine x derivative times cos x, u prime v minus uv prime, so minus sine x times cos x derivative divided by cos squared x, u prime v minus uv prime divided by v squared. And then this is cos x times cos x, which is cos squared x, minus sine x times cos x derivative. Cos x derivative is minus sine x divided by cos squared x. Now this one can be written as cos squared x plus sine squared x divided by cos squared x. Cos squared x plus sine squared x means 1, so 1 over cos squared x. Okay, so that's it. So we showed tan x derivative is 1 over cos squared x, which is same as 1 plus tan squared x for every x in the domain of tan x. All right, so similarly, we can do the formula for cot x. So number 10, f of x equals cot x. Then we can say that f prime of x is equal to minus cosecant squared x, which can be written as minus minus 1 plus cot squared x, or it can be also written as minus 1 over sine squared x. So derivative of cot x is minus cosecant squared x, which is same as minus 1 over sine squared x. Okay, so this one, the proof is that we leave it as exercise, very similar to tan x. We did the one for tan x. For cot x, you can do it as an exercise. So let's look at an example. Let's say y equals x times tan x plus cot x divided by x squared plus 1. Find dy to dx. So dy to dx. See, for y itself is addition of two functions, addition of this function and this function. So derivative of addition of two functions is the addition of derivatives. So I have to add the derivative of this function plus derivative of this function. So this is going to be x times tan x derivative plus cot x divided by x squared plus 1 derivative. Now x times tan x derivative is product of two functions. So derivative of product of two functions is what? U times v derivative. What was it? Product rule. Product rule helps us to find derivative of product of two functions. U times v derivative is u prime v plus uv prime. So then it's going to be x derivative times tan x plus x times tan x derivative. And then u over v derivative is u prime v. So cot x u prime v minus uv prime, so minus x squared plus 1 derivative times cot x, and then divided by x squared plus 1 to power 2. U prime v minus uv prime divided by v squared. Now x derivative is 1, so tan x plus x times, so tan x derivative is secant squared x, right? X derivative is 1 times tan x plus x times tan x derivative. Tan x derivative, we already showed is secant squared. Plus, now this guy here, cot x derivative is minus cosecant squared, so it's going to be x squared plus 1 times minus cosecant squared x minus 2x times cot x divided by x squared plus 1 the whole squared. Now I can take this minus out because this one has a minus, this one also has a minus. So I can take it out. So then it's going to be tan x plus x times secant squared x minus x squared plus 1 times cosecant squared x plus 2x cot x divided by x squared plus 1 the whole squared. So this is derivative of y. So if this is y, this will be derivative of y, or dy to dx. Okay, so let's look at the next example. Let f of x equal secant x. Find, let's say, f double prime of pi. Find f double prime of pi. So f double prime means second derivative of f at pi. So how did we define the second derivative? If you remember, second derivative was defined as the derivative of the first derivative. So first we need to find the first derivative of f, or in other words, f prime of x. First we need to find f prime of x. Once we have f prime of x, then we can find f double prime of x, which is derivative of f prime, and then we can replace x with pi. Okay, so first so solution, first find f prime of x. F of x, what is f of x? F of x is secant x. What is secant x? 1 over cos x. Secant x is 1 over cos x. So what is f prime of x then? F prime of x will be 1 over cos x derivative. Now, u over v derivative, what is it? U prime v minus u v prime divided by v squared. So 1 derivative times cos x minus 1 times cos x derivative divided by cos squared x. And then this is 1 derivative is 0. 0 times cos x is 0. So minus 1 times cos x derivative. Cos x derivative means minus sine x divided by cos squared x. So this is sine x divided by cos squared x, which can be also written as sine x over cos x divided by 1 over cos x. And sine x over cos x is tan x. 1 over cos x is secant x. So see, what did we show here? We showed that derivative of secant x, if f of x is secant x, derivative of secant x is tan x times secant x. So we showed secant x derivative is equal to secant x times tan x. Okay, so this is for the first derivative. Now, what about the second derivative next? We need to find f double prime of x, and f double prime of x means derivative of f prime of x. So here f of x is secant x, so f double prime of x is equal to derivative of f prime of x. And what was f prime of x? Our calculation shows that f prime of x is this guy here, secant x times tan x. So secant x times tan x derivative. And what is that going to be? That's going to be secant x derivative times tan x plus secant x times tan x derivative. Secant x derivative. So we already, now this one, secant x derivative we just showed here. We just calculated here is secant x times tan x. So let me replace secant x derivative by secant x times tan x. And then there's another times tan x here. So times another tan x plus secant x times tan x derivative What was tan x derivative? One of the rules before, tan x derivative we said is secant squared x. So times secant squared x. So what is that gonna be? Secant x times tan squared x plus secant cube x. Or if you want, you can take secant x common times tan squared x plus secant squared x. And secant squared x, because one secant x I took as a common factor, so secant cubed, then if I take secant x out, secant squared will be left. And secant squared is 1 plus tan squared, so I can replace this with tan squared x plus 1 plus tan squared x. Secant squared is 1 plus tan squared, and therefore this one is secant squared, secant x times 2 tan squared x plus 1. So this is the formula for f double prime of x. Now, what do we want to find here? The question asks us to find f double prime of pi. So what is f double prime of pi? F double prime of pi is equal to secant pi. This is f double prime of x. So f double prime of pi is secant pi times 2 tan squared pi plus 1. Now tan pi is 0, right? So it's going to be secant pi, and secant pi means 1 over cos pi. Uh, 1 over cos pi, and cos pi is minus 1, 1 over minus 1, which is minus 1. So the answer is minus 1. Okay, so this is for this example. Now let's look at the next rule. So this was rule number 10. So rule number 11, derivative of exponential functions So I want to derive the derivative of e to the x first, where e is the Euler number. So let me give you a recall. And the Euler number e is defined as follows. So e, we can define it as limit, let's say 1 plus t to power 1 over t as t approaches to 0 plus. Okay, so limit 1 plus t to power 1 over t as t approaches to 0 plus. For example, if you want to look at the right-hand side, so right-hand side, if t goes to 0, the base will go to 1 and the power will go to infinity. So 1 to power infinity, many people think that it's 1, but 1 to power infinity is one of the indeterminate forms. Okay, so 1 to power infinity, please remember, is indeterminate form. So note, right-hand side is a limit of the form 1 to power infinity, and 1 to power infinity is an indeterminate form. So here you can replace some numbers, substitute some numbers for t. T approaches to 0 plus, right? So for example, let's say if t, for example, is 0.1, then we will have, just replace t with 0.1 here. Then we will have 1 plus 0.1 to power 1 over 0.1. So that means 1.1 to power 10. How much is 1.1 to power 10? So that is almost 2.5937. If t is equal to, so remember t approaches to 0 from right, so it could be 0.1 first, then I can replace t with, let's say, 0.01, then I'll get 1 plus 0.01 to power 1 over 0.01, and that means 1.01 to power 100. How much is 1.01 to power 100? That's going to be 2.7048. And if t is, let's say, in the next level, we can say 0.001, then we'll have 1 plus 0.001 to power 1 over 0.001, and that's going to be 0.001 to power 1000. So that's 1.001 to power 1000. That's 2.7169. Okay, so as you can see, the answer, so we are calculating something of the form 1 to power infinity, but the answer is not 1. The answers are not approaching 1. Look at the answers, 2.59, then 2.70, then 2.71, right? So as t approaches to 0, gets smaller and smaller, the outputs get closer and closer to a fixed number called E, the Euler number. So the outputs do not get closer and closer to 1. So the limit is not 1. They get closer and closer to this Euler number E, which is how much? So that's an irrational number, but if you want to write it in some decimal, some estimation for E, so as t gets closer and closer to 0, the outputs get closer and closer to E, which is an irrational number. It's an irrational number and can be estimated as 2.718281. So 2.72 if you want estimation up to 2 decimals, but you know the decimals continue forever. It's an irrational number. But if you want an estimation, like I said, up to 2 decimals, you can say 2.72. So that's Euler number. So Euler number is this limit here. So please remember, 1 to power infinity is not 1. It's an indeterminate form. Now, if you have 1 plus t to power 1 over t, then the answer will be E. So this Euler number E can be also defined in an equivalent way, another equivalent way. So equivalently, the Euler number E can be defined as follows. Another equivalent definition for E is that you can write E as 1 plus 1 plus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, plus dot, dot, dot. So again, here 2 factorial, 2 factorial means 1 times 2, which is 2. 3 factorial means 1 times 2 times 3, which is 6, and so on. Okay, so here, if you look, 1 plus 1 is 2, then this is 1/2, so 2.5. Then this will 2.5 plus 1 over 6, then plus 1 over 24, right? So if you add these numbers again, you will see that the outputs get closer and closer to this number E, which is like almost 2.72. So again, the first at the beginning you're at 1, then at 2, and then 2.5. So 2.5 is already almost close to 2.72, but not very close. But once you add these additional terms, you add with 1 over 6, you will see that the answer will get closer to 2.72. Still not there, but closer. When you add it with 1 over 4 factorial, which is 1 over 24, then you will see that the answer again is even closer to 2.72. Again, still not there, but closer compared to before. Then you add it with 1 over 5 factorial, which is 1 over 120. Again, the answer will be even closer, and so on. Okay, so this is how the Euler number E is defined. And more generally, e to the x is defined as, can be written as, not defined, but can be written as e to the x 1 plus x squared over 2 factorial x squared over 2 factorial plus x cubed over 3 factorial x to the power 4 over 4 factorial plus dot, dot, dot. See, this is consistent with this formula here. If you replace x with 1, then you get what? E to the power 1, which is E 1 plus 1 plus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, and so on. If you replace the power x with 1, here, replace x with 1, then you will get this formula. So this is the definition, equivalent definition of E, and it can be shown, we didn't prove, but it can be shown that e to the x can be, for any number x, can be written in this form. And in particular, if let's say h is a small number, a small number, I mean something close to 0, then what can we say? Then we can say e to the h, again, is of course 1 plus h squared over 2, and then h cubed over 6. But then these numbers will be very small, right? If h is already small, let's say h is 0.1. Then 0.1 to power 2 will be even smaller. 0.1 to power 3 over 6 will be even smaller. So I can ignore these terms, right? Because these will be small compared to the first terms, right? So these terms will be negligible. compared to previous terms. So that's why I can replace this with 1 plus, I can say this is almost equal to 1 plus h squared over 2. Well, it's obvious that this term itself is smaller or negligible compared to these three terms. But why can I say that the addition of not only this term alone, but even when you add it with all the next terms, still the whole result is negligible compared to the previous sum. So this whole sum, although there are infinitely many terms here, because this sum continues forever, right? So plus then h to the power 4 over 4 factorial, then plus h to the power 5 over 5 factorial, and so on. So although it seems that there are infinitely many terms, but still addition of all these terms from h cubed over 3 factorial all the way to the end, still this sum is negligible compared to the addition of the first three terms. So why is that true? Again, I don't want to go into details of the proof. So here, I want you to accept a few things from me. So one is that, well, this is the definition of E. Well, we just need to accept the definition or equivalent definition of E. And then please accept that this definition can be generalized for e to the x this way. And if h is small, then of course e to the h can be written this way, which was immediate conclusion of this formula. But then please also accept that the addition of this term plus the next terms will be negligible compared to the addition of the first three terms. So I can say that this is almost equal to 1 plus h squared over 2. Okay, so now we want to go back to the topic of differentiation. So for differentiation, so let's say let y equals e to the x. Then let's say f of x equals e to the x. Then f of x is differentiable at every x, and f prime of x is equal to e to the x itself. And f prime of x is equal to e to the x itself. So e to the x is a very interesting function in this sense. See, so far the derivative of functions that we have seen were not same as the original function. For example, derivative of sine x was cos x. Derivative of x squared is 2x, right? So not same as the original function. But e to the x has the very interesting property that derivative of this function is the function itself. The original function is e to the x, derivative is also e to the x. So that's very interesting. So far, the only function that had this property that we have seen this before was constant function 0. Constant function 0 also has this property that derivative of, because derivative of any constant function is 0. So if your constant function is 0, derivative of that function is also 0, which is same as the original function. But if you want your function to be non-zero, then that's the only answer so far, that e to the x has the interesting property that its derivative is the original function. Other than this function, you can show that other than this function, if you multiply this function by a constant, like 5 times e to the x, that function also has the same property that f prime of x will be same as f of x itself. So in other words, the only functions in the world that derivative of that function is same as the original function are functions of the form, let's say some c times e to the x, some constant c times e to the x. If your function is some c times e to the x, then the derivative of f will be f itself. And that's the only type of function in the world that has this interesting property. So e to the x, or a constant times e to the x, has the interesting property that derivative is same as the original function, and that's the only type of the function in the world with this amazing property. So if f of x is e to the x, then f of x is differentiable for every x, and f prime of x is equal to e to the x. So let's look at the proof. So what do we need to find? F prime of x is, as we know, it's limit f of x plus h minus f of x over h as h approaches to 0. And then this is equal to limit e to power x plus h minus e to the x divided by h approaches to 0, right? Because f of x is e to the x. So f of x plus h will be e to power x plus h, and then minus e to the x over h. Now, exponential functions have this property that, you know, e to power x plus h, how can I write it down? I can write it as e to the x times e to the h minus e to the x divided by h. Right? E to the x plus h is e to the x times e to the h. Because we know that if the base are the same and you multiply two numbers with the same base, then you have to add the powers. So e to the x times e to the h is same as e to the x plus h. Now I can take e to the x as a common factor, e to the x common factor, then what will be left? E to power h minus 1 will be left divided by h approaches to 0. And then e to the h, what was e to the h? So we already saw that. So let me call this formula, let's say formula star. E to the h is almost 1 plus h squared over 2 factorial. So when you take the limits, we can say this is limit e to the x times 1 plus h squared over 2 factorial, or 2 minus 1 divided by h. H approaches to 0. So here it's there is an estimation. Okay, let me see. It seems that the screen is freeze. Okay. Yeah, here I used e to the h, the expansion for e to the h. Which is this function here. Here I replaced it here. But another technical thing here is that here I have equality, but here I have estimation sum. But because h approaches to 0, it can be shown that, you know, the rest of the terms, when you take the limits, the limit of those will be also 0. So I can replace the estimation with equality here. Okay, so because the rest of terms are negligible and their limits will be 0. So again, please accept that I don't have to write estimation. I can just write equality here. So again, I don't want to go into too many details. Just please accept that because I'm taking the limit and h approaches to 0, estimation can be replaced with equality because the remaining terms in limit will be 0. So if there was no limit, I had to write estimation, but when the limit as h approaches to 0, the other terms will go to 0, and therefore the estimation can be replaced with equality. So just please accept it. I don't want to go into details. You know, these, if you take an analysis course, then we have to justify every little step And but here in this course, calculus course, it's more focused on computations rather than proofs. So that's why I may skip some justifications for some steps. So here, e to the h, we replace it with this function here, and therefore I can write this one as limit e to the x times h plus, so 1 minus 1, they cancel. 1 and minus 1, they cancel. So I'll be left with h plus h squared over 2 divided by h approaches to 0. And then I can write this one as limit e to the x. I can take h out. 1 plus h over 2 divided by h. H cancels. E to the x, I can also take it out. Limit 1 plus h over 2. H approaches to 0. Okay, so then this will be e to the x times 1 plus 0. As h approaches to 0, this goes to 0. So 1 plus 0, and then the answer is e to the x. So we showed f of x equals e to the x is differentiable. And what else? And f prime of x is equal to e to the x. Okay, so let's look at an example as well. Let's say that y equals x times e to the x. X times e to the x. Find all points on the graph of y equals f of x. So let's say this is f of x. Find all points on the graph of this with horizontal tangent line. Horizontal tangent line. Okay, so in the exam, it's possible that I give you the function and ask you to find the derivative of the function. Well, that's very straightforward. But sometimes, we could change the wording a little. So instead of asking the derivative directly, I can ask the slope of tangent line, which is still derivative because we know derivative at any point is the slope of tangent line at that point. Or I can again change it a little bit further, and I can ask you, for example, with points with horizontal tangent line. Horizontal tangent line means slope of tangent line must be 0, which means derivative must be 0. So in other words, I'm asking you to find the roots or solutions of f prime of x equals 0. Again, why is that? Because let me write it down for you. So horizontal, the solution, horizontal tangent line means what? Means a slope of tangent line is 0. Horizontal tangent line means slope of tangent line is 0 because the slope of a horizontal line is 0. Or if you have a horizontal line, the slope will be 0. And this is same as saying or asking for f prime of x equals 0. Because slope of tangent line means f prime. Slope of tangent line at any point x is f prime of x. So if you want slope of tangent line to be 0, you want f prime of x to be 0. So in other words, we want to find the solutions of f prime of x equals 0. So what is f prime of x here? F of x, what is f of x? F of x is x times e to the x. So f prime of x will be, I have to use product rule. Product rule says what? U times v derivative is u prime v. So x derivative times e to the x plus uv prime plus x times e to the x derivative. So then this is going to be 1 times e to the x plus x times e to the x. And the answer will be e to the x times x plus 1. So again, the screen is freezed. Stop share and share again. Okay, so we use the product rule. X derivative times e to the x plus x times e to the x derivative. 1 times e to the x plus x times e to the x. So that's going to be e to the x times x plus 1. So that's it. So this is f prime of x. And lastly, we have to solve for f prime of x equals 0, right? So this is the formula for f prime of x. But remember, we wanted to find the points with horizontal tangent line, which means finding solutions of f prime of x equals 0. So lastly, find the solutions of f prime of x equals 0. Then we get e to the x times x plus 1 equals 0. But e to the x is always not equal to 0 because exponentials always positive. Always positive. So then this means x plus 1 has to be 0, right? Because product of two numbers 0. So either first one is 0 or second one is 0. But first one is non-zero because exponential is always positive. So second one must be 0. That means x plus 1 must be 0. And that means x equals minus 1. And therefore the point, so which point has horizontal tangent? It says find all points with horizontal tangent lines. So which points have horizontal tangent lines? Well, the x value, when it says point means you have to find x and y coordinate. But x coordinate is minus 1. So we can find the y coordinate easily now. Thus, the point on the graph of y equals f of x with the horizontal tangent line is, what is it? Well, the x value is minus 1 and the y value should be f of minus 1, right? Because see, if you have your x value and you want to find the point on the graph, well, you just need to plug the value of x into f and then you will find the y coordinate, right? So if x value is a, the y value will be f of a, right? So the point on the graph with x value of minus 1 will be minus 1 and f of minus 1. And what's that going to be? Minus 1 and f of minus 1 means minus 1 times e to the power minus 1. Because remember, f of x is x times e to the x. So f of minus 1 is minus 1 times e to the minus 1. And then this is minus 1 and minus 1 over e, right? Because e to the power minus 1 means 1 over e. So minus e to the power minus 1 means minus 1 over e. And note that the question does not ask, but if the question also asks for the, let's say, equation of this horizontal tangent line, what's that going to be? So note the equation of this horizontal tangent line will be what will it be? The equation of the horizontal tangent line, y minus f of y0 equals f prime of x0 times x minus x0, right? So y minus f of y0 is, this is my point. This is my x0, and this is my y0. So y minus 1 over e equals f prime of x0 is 0, right? Because how did we get this point? By solving f prime of x equals 0. We started with f prime of x equals 0. We found this x value, or this is my x0. So this x0, of course, has the feature that f prime of this x0 is 0 because it's the solution of this equation. So if this is the solution of this equation, means f prime of this point must be 0. F prime of x0 must be 0. You can also verify it if you want, because f prime of x is x plus 1 times e to the x. So if x is minus 1, but of course, f prime of x will be 0. Minus 1 plus 1 is 0 times anything is 0. But even without calculation, we know that f prime of x0 must be 0 because x0, this number, is the solution of this equation. So the right-hand side becomes 0, and therefore the equation of tangent line becomes a minus 1 over e, which is a horizontal tangent line at which point? At x equals minus 1. Okay, guys, so today we learned some derivative rules. We learned derivative of different types of function. The last thing we did, derivative of exponential functions and derivative of e to the x, which is e to the x itself. And yeah, next time we'll continue with more derivative rules. Okay, guys, so thank you and see you next time.